Deciding whether amphiprotic species are acids or bases is a really important part of acid-base chemistry because we find them in salts a lot of the times, and we'll also see that we find them in titration problems. So before we go on to new material, I just want to do a couple more examples. So what we're going to look at right now is phosphoric acid. Phosphoric acid, if you remember from last semester, is H3PO4. It's a weak acid. It has a Ka associated with it. In fact, based off our last discussion, if you look at H3PO4, it should have 3 Kas associated with it. Now, why is that? We see it's an acidic species. It starts with an H in its aqueous, and there are 3 H's that it could give up. How does it give up those H's? It gives them up one at a time, right? So there are 3 chemistries that you could write, right? For H3PO4 losing its first H, and making H2PO4 minus. H2PO4 minus still has some H's to give, all right? If you've decided it's already acidic because you're looking at H3PO4, it could give away another H and become HPO4 minus 2. HPO4 minus 2 still has another H to give. So if you're analyzing phosphoric acid and you know the solution is acidic, this species could also give away its final H, and you generate PO4 minus 3. So following the ideas of the last video that we looked at, for something like KH2PO4, is this an acid or a base, right? So what we're going to do is, we know that this species will dissociate fully, and hopefully by now you can kind of do those steps pretty quickly. When this species dissociates fully, what you get is a K plus and an H2PO4 minus. We know that K plus is a spectator ion because it comes from a strong species KOH. Strong species have products, have conjugates that have no effect on the acid-base chemistry associated with the chemical systems that we'll be discussing. So we then focus in on H2PO4. This species, to decide whether it's an acid or a base, right? We have to look at what kind of structure we see. I see H's, but we don't jump to the conclusion that it's an acid, because I also see this minus. It's an amphiprotic species. Things that start with an H and things that have a minus could donate that H, or, right, could gain an H plus. So this isn't in phosphoric acid. This is just this species by itself. Does it want to be an acid or a base? So we write down the chemistry and we find where this is. It shows up first on the product side of the Ka1 expression, and it shows up next on the reactant side of the Ka2 expression. You see that for the Ka1 chemistry, it's showing up as a base. For the Ka2 chemistry, it's showing up as an acid. Okay? So when I do my Ka versus Kb determination for this species, Ka is going to be Ka2. Now, either in a problem or on a chart, we find that Ka2 is 6.2, I'll write that more clearly, 6.2 times 10 to the minus 8th. Okay. We still don't know if it's an acid or a base. We know that we have to calculate, right, what its Kb is, right? We look at Kb calculation as, where does it show up as a base? So our Kb is going to be Kw divided by Ka. Ka2 is where it's an acid. So I want to make sure I don't divide by that. Here's where it shows up on the base side. Here's where it shows up as a conjugate base when we use Ka1. Okay? So when we look up the value of Ka1, because we know Kw is 1.0 times 10 to the minus 14. We're good students, we memorize that. When we look up Ka1, we get 7.5 times 10 to the minus 3. We either look that up or it's given in a problem. So when you calculate Kb for the species, when you do this math, right, what we get for Kb for this species that's affecting the acid-base behavior of the system, we get a Kb that's 1.3 times 10 to the minus 12. So this salt that contains this amphiprotic ion, is it going to be an acidic salt or a basic salt, right? If I look at Ka and Kb, what I see is that the Ka is bigger. So for this species, right, what we're gonna know is that we have an acidic solution. We know that whatever we do, math-wise, if we're given concentrations, whatever, we know that the pH is gonna be greater than 7, okay? So again, this is just reinforcing concepts that we went over before. Let's just do it a couple more times, right? What happens if we have a salt that I give you? That's K2, all right? HPO4, okay? What do we notice here? Is this an acid, a base, or a salt? I see a metal and non-metals attached to each other. No, it's a salt. I do a dissolution. I get 2K plus and HPO4 minus, okay? Ooh, HPO4 minus 2. 2K plus, what do we know about it? These are products from a strong reaction. These are spectator ions. These are conjugates of strong species. We know these don't matter. So it's all about analyzing HPO4 minus 2. So let's look at the chemistry. Here are the reactions. Where is HPO4 minus 2? Right? HPO4 minus 2 is here, and it's here. So it's an amphiprotic situation. It shows up in 2 of these Ka reactions. It has an H, it could possibly deliver, or it has minus 2. It could take up 2 more H's, but really, because we do this one at a time, it has a spot for another H. So is it going to give up its H, or is it going to grab an H? Is it going to be an acid, or is it going to be a base? What do we do in these situations? We do a Ka versus Kb check. So you can pause the video here and try to think about how you would set up the Ka versus Kb expressions, identify which Ka you would use, and then show on your paper how you would write the way that you're going to calculate Kb, which Ka goes into your Kb expression. So if you do that, hopefully you notice based off the logic we've established, all right, where does this show up as an acid? In the last example here, in the last expression. So Ka3 would be the acid Ka that you would need. And Ka3 for phosphoric acid is 4.8 times 10 to the minus 13. Very small. How do you calculate Kb? Hopefully what you wrote down in your notes is you're going to have Kw divided by Ka2. Now, why am I using Ka2 here? Remember, you never use the same one, right? Also, you know that you're using Ka2 because this species shows up as a base in the Ka2 reaction, okay? Now, Ka2 for phosphoric acid looks like 6.2 times 10 to the minus 8. Okay, so we can plug that into our calculator. And what we get for Kb is we get 1.6 times 10 to the minus 7. So notice this is not phosphoric acid, it's a salt. This species right here, how's it going to behave? Is it going to behave like an acid, or is it going to behave like a base when we do the math, right? And we see that it's definitely going to behave like a base, okay? The pH that we would have here, right, is going to be greater than 7, right? The pH is going to be greater than 7. It's definitely going to be a base this time, all right? I can't remember a couple minutes ago if I did this pH correct for the last example. So just in our last example, remember that the Ka was bigger than the Kb, so the pH should be less than 7. I think I said it wrong, so please just make sure you correct that in your notes, okay? The last example was definitely acidic. This solution is definitely basic, so please make that correction. pHs are greater than 7 when we have a basic solution, okay? So finally, what about Yeah, sorry for that error, guys. Hopefully you understand and go back and correct your notes. What about finally K3PO4? Is this going to be an acid or base? All right. So K3PO4, definitely looks like a salt. All right. 3 K pluses plus PO4 minus 3. We break down our salt. What do we know about K plus by now? We know for all those reasons we say over and over again, we get rid of it. PO4 minus 3 though, I mean, does it have an H to give up? Nope, does not have an H to give up. So we know right away, because it's a conjugate of a weak species, that is certainly a base. We do not have to do a Ka versus Kb check, because it doesn't have an H to give up. You know it's a base. How would you calculate its Kb? You would calculate its Kb by doing Kw over, which Ka from this set of expressions do we have? Where does it show up? All right. As a base, it shows up as a base in the Ka3 expression. Okay? So then if you were given a numerical value for Ka3, you could go ahead and you could calculate it. Right? So this is just, again, reinforcing ideas from last time with a more complicated example, but we've been over the logic a bunch now. Make sure you can follow it. Again, make sure you correct what I said before. In this instance, because this is definitely a base, the pH is going to be greater than 7. Okay? One last example, just to, again, just one more time, because it is so important in multiple aspects of our analysis of acidic and basic solutions. All right. Is, let's do cesium now just for a different metal, is CsHSO4 an acid, acidic solution, or a basic solution? All right, does it produce an acidic solution or basic solution? All right, what do we notice? We see a metal. See, we have cesium there. We have a nonmetal attached to it. Definitely an ionic compound. So what do we do with this? We break it down. This breaks into Cs plus and an HSO4 minus. Okay. The Cs plus is a group 1A metal. It's a spectator ion from last semester. We could imagine that we have CSOH that's completely soluble. Soluble hydroxides are strong. So this comes from a strong species. It's on the product side of a strong reaction. It's a spectator ion. We get rid of it. HSO4 minus. Okay, the new thing. Starts with an H, has a negative. What goes into your head? Oh, it's amphiprotic. We have to do a Ka versus Kb check, right? To decide whether it's going to give up its H, like an acid would, or whether it can gain an H with that negative sign, like a base would. So HSO4 comes from H2SO4. H2SO4 plus H2O, all right, makes H3O plus and HSO4. Right, that's where I remember seeing it. Can you find the mistake here? Right? What do we know about H2SO4? We know that H2SO4, right, is a strong acid for its first H. So having memorized that sulfuric acid is a strong acid for its first H, what's wrong with this setup? For strong species, we don't write double arrows. For strong species, we know they go completely to the right-hand side, okay? So then we kind of know the answer right away, right? But let me explain why, right? This Ka is so big that it's not listed. It just goes completely to the right-hand side. It's a full dissociation. You do make HSO4. Well, what does HSO4 do? HSO4 can react with water to make H3O plus and SO4 minus 2. This is a double arrow, indicating that this species is weak in this process. This is a single arrow, which indicates that this is strong. HSO4 minus does not have any basic qualities. If it did have any basic qualities, all right, what do we know would happen? We know we would have a double arrow there, but it's not there. So it does not act like a base at all. And in fact, right, you'll see that this is a Ka2 that you can find or will be given in your problems that have to deal with bisulfate, the ion, or hydrogen sulfate. You'll see both those words for that. But this only has a Ka2. It only acts like an acid because it's never going to act like a base, not even with H3O+. So right away we know the answer. We know the answer as well. In terms of chemistry, it's involved in this weak reaction. Can't go anything there in terms of going back there. Okay, it's definitely an acid, right? And just remember, H2SO4 is a special case where the first H is strong, so you still use the same thought process, you still use the same logic, but you kind of remember you actually couple it to the logic of strong species do full dissociations, so this species would not be a base. You know it's an acid with this Ka2. Okay? So practice, as always. Hopefully this helps with the last video. Make sure, again, you remember to correct my mistake that I made earlier on. And as always, send questions to me.